me ask for the viewers here, what is the difference in statistics between data and complex data? Like, where is there the beginning? In just a little short overview, please.
Yeah, so let's make a simple example. So suppose I measure the blood pressure of a bunch of people, and I want to, from that, predict some other health measure, like some blood measurement. And you can picture that as just simple plot, where on the x-axis I have blood pressure, and the y-axis I have some other health measurement, and then I just have this scatter plot. And you want to be able to describe that trend, that relationship, and the simplest way to do it is to put like a line through the data, and that's called a linear regression, and that's a very, very simple model going back hundreds of years, but it works surprisingly well in a lot of problems. If the data look very nonlinear, if it doesn't follow a nice linear trend, then that simple method is not going to work, and that's when we use what you've alluded to there, called non-parametric inference, which just means we're not restricting ourselves to simple functional relationships. We're going to allow very complicated relationships between the two things. But then data can get far more complicated. Now imagine I'm trying to predict whether you're going to get a certain disease based on measuring thousands of your genes. And so now all of a sudden there's thousands of variables. There might be more variables than there are subjects in a study. And now you're into this realm of very complex data, and we have to use much more complicated techniques.
And you developed one of the methods that makes this easier or possible, huh? Do you understand it correctly?
I did. I've developed.
Researched it. I mean, research.
Yeah, I wouldn't say I don't. Yeah, I've done a lot of research on the techniques. So what ends up happening is typically people will come up with techniques for analyzing data, often very, very done very heuristically or intuitively. And then you want to say, well, what are the mathematical properties of these techniques? When are they reliable? And that's the kind of a lot of the work I've done is to develop the properties of these methods. Now and then someone will come up with a brand new method that turns out to be surprisingly successful, and it can be field changing. I don't think I've ever done that myself. A good example, just to give you an example of this, is my friend Rob Tibshirani, who's a statistician at Stanford. One day came up with this method he called the lasso, which is a way of doing relating some outcome like a disease or some measurement to very large numbers of variables. There's thousands of variables, like genes, for example. And this was a difficult thing to do. And then he came up with a method which you can implement very easily and quickly, and works very, very well. And so that's kind of a field-changing discovery that they don't happen very often, but now and then somebody will come up with something like that. I've been more about studying methods and figuring out their properties.
Interesting question. It's like he finds out new stuff. Is it like just finding a formula, how to use it, or what? How can I imagine it? What would you say to layman is like, how do you find something new in these fields? How does that work?
It's usually through necessity. So let's go with this gene example again. Say I want to say which genes predict whether somebody gets Alzheimer's disease or not. And so I might have 1,000 people in a study. I might have 500 people without Alzheimer's and 500 with, and I've measured thousands and thousands of genes on these people and how strongly expressed are these genes. How can I predict the outcome here, disease or not disease, based on these thousands of genes? There's so many parameters there that I have to estimate. And the idea there was that the Rob Tibshirani came up with was the notion of sparsity, that we might measure thousands and thousands of genes, but really maybe only a small number of them are involved in the disease, and the rest of the genes really have nothing to do with this, or at least they're not very predictive of this. And so we really want a model that's sparse, that really somehow figures out that you really only need to worry about a small number of genes. He expressed that as a mathematical optimization problem. And that problem had the problem that he wrote down had a certain property known as convexity, which is just a nice mathematical property. Convexity is kind of a dividing line in the world of optimization, that things that are satisfy this property of convexity turn out to be things that you can often solve very quickly, and things that are non-convex are very hard to solve. And he came up with this optimization problem, which was convex, and so you can solve it very quickly, and it leads to a way of doing prediction that's very fast and very often quite accurate.
Cool. It's cool. So, okay. So convexity means like how closely and how easily it is connected and has to do with the result. Am I understanding that correctly?
Well, it has to do, in some sense, you might say, with the shape of the problem. So if I were to draw a curve like this, that's a convex function. Whereas if I drew a curve that looked like this, that's a non-convex function. And it's a little bit harder to picture these things because we're really dealing with things in high dimensions. But this convexity just makes most problems easier, both to study mathematically and to implement computationally. I mean, people in AI especially have made incredible progress dealing with non-convex problems, surprisingly. That's one of the things that's been really making a lot of these AI things work, is that they have found ways of optimizing things that are very non-convex. But whenever possible, we always try and hope to express something as a convex problem just because it makes it easier.
Okay, cool. Good. If you like this clip, watch another one. And if you want to see the whole interview, click here.